All right, the last talk of game developer session is here, and it's about Decima Engine. Well, in Horizon Zero Dawn, which is not exactly an indie game. It's quite a huge game, and Leszek Szczepański is here to talk about all the challenges that he faced during the development of Horizon Zero Dawn in Decima Engine, as I said. So Leszek, welcome to Game Developer Session, and please give him a welcome.
My people, sons and daughters of Helgen, for many years we have been a broken nation, shunned, oppressed, and conquered by those that we sought to escape. With these words, 13 years ago, Scholar Visari, an evil dictator, started the first Killzone. And also with these words, the history of Guerrilla Games started. My name is Leszek Szczepański, and I'm a senior gameplay programmer at Guerrilla Games in Amsterdam. And today, I come to talk to you about the technical journey that our studio had to go through in order to create Horizon Zero Dawn. Now, for those of you who might not know, Horizon Zero Dawn is an open-world action role-playing game exclusive for the PlayStation 4. It is set in a lush, post-apocalyptic world where gigantic machines have taken over and humanity is no longer the dominant species. Now, Guerrilla Games is a Sony first-party developer from Amsterdam, and until recently we have been known for the series of PlayStation-exclusive first-person shooters, a series known as Killzone. And during this time we created 6 games for 5 different platforms, and that means that we've been making first-person shooters for over a decade. But as the prophecy said, something needed to be changed. And after months of pitching, proposals, and discussion, the project that would eventually become Horizon Zero Dawn was approved. And because of that, we stood before this dramatical change of our technology, tools, methodologies, and also our ways of thinking about game development and game design. It was also almost as if Scholar Visari himself would be standing before us saying they cannot imagine what awaits them. So, history of our engine is pretty much the history of Guerrilla. And although it did go through significant changes over the years, especially during generation switches. The code that we use in Horizon Zero Dawn is based on the code that has its roots in Shell Shock and original Killzone that were released these 13 years ago. And as you can see that until about 2013, we have been using this technology most internally. And at some point, around PlayStation 4 era, we decided to share this technology with other developers to improve our own technology and help them out. And that is the moment where our internal tech has become the Decima Engine. Now, a game engine is a super complicated beast, and there are many ways and angles at which you can look at it, analyze it, and discuss it. And this has been done about our engine. So my friends have been talking about different aspects of the Decima engine before, about rendering, about procedural placement, and also our managing director did a talk at DICE this year about the journey of Guerrilla itself during development of Horizon Zero Dawn. Now, I hope these slides will be available to you guys later on, so these links will be usable. Now, in this talk, I will talk about the changes that we made to our game systems in our engine, which was purpose-built for making first-person shooters, and we needed to create an open-world role-playing game. And I will also evangelize component-based architecture a little bit. Now, let's first have a look about what's the difference between a first-person shooter and a role-playing game from a more technical standpoint. So, first of all, the fundamentals are common. So you have your rendering, you have your sound, you have your threading, and this can stay absolutely the same. However, RPGs tend to have this larger amount of content, and that means that the tools that you need to be much more efficient. You will be churning out much more content, and you need to make sure you can actually do that. Also, because you're touching so much more stuff, you have to be able to save your game in a relatively smart way. What's really important is that a first-person shooter can usually be divided into separate levels. And that means that you tend to encounter less emergent behavior, meaning if you make a decision, if the player makes a decision in level 1, it doesn't necessarily matter in level 2, 3, or 12, right? But that also means that if an error happens, if a bug occurs in level 1, might not matter at all in further levels. However, because in role-playing games you do expect your decisions made by the beginning of the game to matter at the end of the game, that means that a minor bug that might happen at the beginning of a game might inflate over time into some dramatical problem later on. And finally, role-playing games are expected to feature more kinds of types of activities and resources. So we're talking not only about combat, but crafting, quests, conversations, mini-games, and many other. And that means that we as game developers need to build and create and design many more systems to facilitate these new additional types of gameplay. So let's start quickly about the basics, basic concepts that we use in our engine. And none of this will be revolutionary, but it's only so that we are on the same page when we will be talking further. So first of all, conversion. All of our game data in the engine, when we edit it, is stored in a text format. And then when the game runs on a dev kit, it goes through a process we call conversion, which changes this text format into a very highly optimized binary format, which is essentially quickly loaded on the PS4, and essentially that's the thing that ends up on the game disk. Also, conversion is much more than just creating from text data, binary data. It also does things like compiling of scripts, and also it does check for errors as early as possible to find broken content. And of course, the game interacts only with this binary data. Second concept, resources. So all of game data that we use is stored in something we call resources. So essentially these are specific types of C++ objects. And each resource has a unique universal identifier, which we use it to identify it. And resources are read-only. So they are loaded into the game and they are never changed. Now, objects in games that do have their state modified at runtime are called instances. And an instance is essentially defined by a resource or multiple resources, and an instance only holds a pointer or multiple pointers to resource objects. And of course, a single resource can define multiple instances. Thirdly, entities. So I'm sure many of you are familiar with game entities and entity-based systems. So in the Decima Engine, everything in the game that is not simple geometry or just a location marker is an entity. The player is an entity. The camera is an entity. A destructible rock is an entity. And an entity is just a collection of components. So it has on itself minimal data, and its behavior, its functionality, and its looks are defined by the components that it contains. And finally, messages. So in the Decima Engine, we use very typical, almost textbook-like messaging system, like object-oriented messaging system. So objects communicate by sending messages and receiving messages, and these are essentially C++ classes derived from the message type. So for an object to be able to handle a message, it needs to register that fact in its runtime type information. So essentially it says, this message type is handled by this function, and whenever a message is sent, that function will be called. And some objects can propagate these messages further, and that's what we do in entities. So you send a message to an entity, and it propagates the message to its components, and components react to it accordingly, either by providing information or by modifying the entity's behavior. Okay, so let's start. Essentially, let's talk about the first system. Let's start with something simple. So character and skill progression. In role-playing games, it is expected that the player character evolves over time. It gains new skills, new abilities, essentially gets better along with the player. Now, In Killzone, there was nothing like that. Killzone was a typical first-person shooter. You get better by getting a better gun, not by getting a different gun ability. And we need to build something totally new. And in Horizon, these abilities are called perks. And we essentially had two types of perks. One is a passive perk. That means that other systems can query the player entity whether a specific perk has been acquired, and if that's the case, just modify its own behavior. Or we had active perks. So a perk in game data is also a resource, and that means that that perk resource links to component resources. That means that when the player unlocks a specific perk, the component resources that the perk resource links to are added to the player entity. So essentially, unlocking a perk modifies the behavior of the entity by adding specific components to itself. Okay, that is relatively simple. Let's go to something more interesting. Quests. So role-playing games are quest-based games. So we're talking about missions that can take hours or even longer to accomplish, something interesting. And in Horizon, we wanted to have long, complex, and non-linear quests, and we wanted a lot of them. Now, the thing is that in Killzone, we did already have a mission-based system, something which would allow to give player objectives, fail them, or complete them. Now, the problem is that the system was very hands-on, meaning you would need to write a script which would show on the HUD, do this, and you would need to run a script in a state machine to check whether the objective has been completed, whatever that was. And that is indeed very, very flexible, but is not very scalable, is difficult to debug, and very limited in its capacity. Actually, it even caused problems for us in Killzone Shadow Fall. So we need to build something absolutely different. So what we did is that we created a system which defines a quest as a probability space, which is defined by a graph. Each node of that graph is understood as a part of a story, a quest step. And each step is connected to an action that the player needs to perform in order to progress. That action is essentially a message handler. So we have a conversation system sending a message. The player has interacted with this non-player character. Okay. Progress the quest. The combat system, the destructibility system says, player killed this entity. The quest listens to these kind of messages, checks whether appropriate entity has been killed. If that's the case, progresses the quest. So essentially, the quest system itself is a listener to all other game systems and sits at the very top of the whole game. And if you're more interested into that specific system, I did a talk specifically about that at GDC earlier this year, and there is a link to a YouTube video of that in the slide. Again, I hope they will be available to you guys later. So let's have a look at how a quest would be built and how it works. So this is a graph which shows a very simple example quest. What happens in it is that the player approaches a village, and a distressed villager approaches the player, asks for help. Some horrible, horrible menace has infested the fields and made problems for the villagers to harvest crops. So the start node, which you see, is essentially the start of a quest, meaning the quest system is waiting for the conversation system to send a message the player has interacted with a distressed villager. When that happens, there are two options which open before the player, step A and step C. In step A, player needs to eliminate all the insects in the field. So essentially, we are waiting for a message from the combat system to say, these entities have been killed. The quest system checks whether these are relevant entities in this context, and if yes, progresses the quest. In step C, the player has an option to go a peaceful path and maybe talk to the queen of insects and maybe work something out. In this case, we again are waiting for the conversation system to send a message that you have interacted with the swarm queen. Now, what is important in this system is that step A and step C are not mutually exclusive. These are options that open before the player. That means that the player is absolutely free to complete step A, kill everything, and then go to the swarm queen and talk to her, or the other way around. However, if the player decides to go the aggressive path and kill everything, then the option to slay the swarm queen opens before them. And here it's a little bit different. As you can see, there's this red line coming from step B to step C. And that means that if the player decides to slay the swarm queen, the step C will be blocked from the story. It will no longer be available because she will be dead. However, there's no line in the other direction. That means that the player is absolutely allowed to talk to the Swarm Queen and then be an asshole and kill them. And finally, regardless of what the player does, the option to report back to the village and get the reward opens up. And that means that we are listening, again, for the conversation system, or maybe the physics system to say, as we have entered this collision volume, or maybe there is a sequence running, meaning like an animated cutscene, and we're waiting for the end of that cutscene. Essentially, that's the moment the quest ends. And only by defining these 5 nodes, 5 interactions, we have multiple ways to go through this small quest, and in turn, we have many unique player narratives possible. Now, what I'm going to show you is actually a screenshot from our quest editor, and as you can see, the graph I showed you is pretty much what we do in our quest editor. So the nodes that you can see are pretty much representative of the graph which I showed you before. The only difference here is that the boxes inside these nodes define these actions that we are waiting for, and there's also some information about the visual information that we provide to the player at each step of the quest. Okay, we're done with quests. Let's go to another staple of role-playing games, items and inventory. So we needed to have a fully fledged inventory system with containers, item persistence, various item types, and should also allow for trading of items between characters, and it should allow for crafting. Now, in Killzone, we already had item management. The problem was that it was super simple. Everything was either a weapon or a resource, meaning an ammo or armor or health. So there were no containers, no complex item types, and dropping was very limited. The thing is that we already had very elaborate logic for weapons, meaning for damage. And we couldn't just throw it away. It was essentially 10 years of really relatively, okay, good, I shouldn't say shit stuff about my company, should I? It was 10 years of research and development into weapon systems, so we couldn't throw it away. We needed to keep our inventory system, and by turn, we needed to adapt it, and that resulted in some interesting problems. Most important of which is a problem with item persistence. So, what is item persistence? The idea is that if you have a rock, and it is on the ground, and you pick it up, and you hold it with you, and then you drop it, and another entity picks it up, and then puts it in a container, and that container explodes, and that rock falls off, that the game can track that this rock in different states is the same rock. It can actually refer that this is actually the same item logically. And in Killzone, this wasn't the case. So the way it works is that items are also entities. And each item would be represented by 2 different entities. Either the pickup entity, which was the thing lying on the ground, or the equipped entity, so the gun that you would be holding. Now, the problem with this is that one entity gets destroyed, another created, and the only thing they communicate between each other is the amount of ammo. So there is no way to say this is that entity, because that would got destroyed and that's a new one, so it has a different UID and a different location, and everything is essentially different. And that caused problems, because in Quest you want to have your sword of valor or whatever, and be able to refer to it whatever it's happening to it, whether it's in a container or whether equipped by somebody. So the way we approach it is we've exploited our component-based architecture again. So we decided to move all of the state switching to a separate component. So an item would become a single entity, and the only thing that would happen is that a specific item component would have 2 lists of additional components. And whenever item is dropped, a set of components would get removed, which is specific to being equipped, and a bunch of components would get added, which are specific to being on the ground. And when the item would get picked up, these components would get reshuffled again. And there was, also, of course, some set of common components. So essentially, by doing that, every item, regardless of its state in the world, would stay a single entity, which is easily trackable through the world. So how do we approach containers and merchants? No, that's also relatively simple. Inventory is also a component. So it holds all the logic related to storing, equipping, dropping, and picking up items. So after some cleanup, every entity could become a container. So even a chest, like a simple 3D model or a robot could carry that component and in turn carry items. So just by simple cleanup, we managed to get chests, awesome, and then we needed to have merchants. And essentially, we derived from our inventory component, our merchant component, which still has all the inventory logic, but also has information about item exchange values or the time in which a stock gets renewed. Okay, another system, conversations. So we need to create a system that would allow for the player to engage in interactive conversations. I mean, in every RPG, there is a conversation system. I mean, why kill the dragon if you can seduce it, right? So the problem was that in Killzone, we already had multiple ways to get characters to talk and act, but there was no way to make it automated. So we needed to figure something out. So in Killzone, it was possible to have entities, including the camera, act in a scripted way. So all the actions that they would perform were put on a timeline, and according to the ticks of the clock, they would perform these actions. That's a feature that we called sequences. So for Horizon, we built a superstructure over that, something that we called sequence networks. So essentially a graph of these sequences. And the way it worked is that we could control how each sequence how next sequence plays after the previous has finished. So we had like branching logic. So you could say there is a list of these different sequences and they play in a random order, or there is a condition which runs a script and checks which should be the next sequence. Or we could also have breakout logic. So you could, in the middle of a sequence, say when that happens, you just go to a different one. So essentially we build a network and or graph of these sequences. We also managed to improve over the system. So we managed to generate these sequences from text, including and stuff like voiceover, camera positions, and gestures. And that generation was used pretty much for every first pass of most conversations. Now, what I'm going to show you is the screenshot from our sequence editor. And as you can see, these are these blocks on the timeline, and they define either entities which are taking part in that sequence, or the actions they need to perform. And what you are seeing here is a sequence network. So essentially, the white nodes that you see are the sequences themselves, and all other are these flow controllers, so conditions, branches, and so on and so forth. So pretty much every conversation in our game looks like this. Sequences linked by branching or flow logic. Okay, scripting. Now we get to the real stuff. So in every game nowadays, you need a scripting solution. You need to give the designers power to build complex logic, but you don't want to flood them with C++ or stuff which can get really complicated and it's not very handy. So we needed a scripting solution fit for a massive open-world role-playing game. So scripts needed to run efficiently, be debuggable, and not be very complicated to use. And in Killzone, we already had a Lua-based solution, but Lua is slow, it's difficult to debug, and it's really easy to make mistakes. One of the major issues we had with Lua is that every game object that was referenced in the script was referenced by its name. So somebody made a typo, and you would only catch the error when the script runs. And the iteration time with that kind of logic is atrocious. So we needed, again, build something totally else. First of all, in Killzone Shadow Fall, we tried to work around the issues. So we built a special editor for our Lua scripts. And the boxes that you see here are essentially visual representation of Lua scripts. So essentially this is a state machine which is defined by a bunch of scripts, and we can visually edit these scripts. Plus we have some sort of information in the editor about the game objects you're referring to. So you don't need to type the names, they're just being taken from game data. So that was in Shadowfall, but it was still not good enough for Horizon. So what we did, we decided to start from scratch, and we decided to build our custom visual scripting language. So the way it works is that essentially you're building a graph. And each node of that graph is a C++ function. It's essentially a one-to-one relation between a C++ function and a node in that graph. It was also possible to reuse sets of nodes as sort of functions, which were defined by whatever designer was building a script. And during the conversion process, all these scripts would be transformed into text and then compiled by Clang into dynamic libraries. And these dynamic libraries would be loaded into the game at runtime. So essentially what was happening is that suddenly we are running native code, which is so much faster, and we have a compilation step in our scripting language. Perfect. So the way it looks is that this is actually an example node. So the source code which you see is a simple function that is used for finding a quest item on an entity. And the node that you see underneath is essentially the visual representation of that function. So these things are equal. So during our conversion process, these nodes will be translated to that kind of code. What you see here is our script editor. So if anybody who works with Unreal, this is quite similar to Unreal. And so essentially nodes are functions, you have flow control, you have data flow control, and every now and then this function is run and does something. This is some sort of a sound function, if I remember correctly. Another interesting thing is because game designers like state machines, we also built a state machine editor on top of our script editor. So in game we can have state machines attached to entities or to scenes, and a concept I will talk about in a moment. These are edited like this. So each node here is a set of scripts. And each node here can also handle messages which are sent from different systems. So either a player can enter a collision volume, and the script can react to that and can run a script and essentially change the state of a state machine if needed, or perform some other action. Streaming and world management. So the problem that we were facing was simple. We wanted to have a big open world and not run out of memory. So in Killzone, the system that we had a streaming system, but it was actually quite simple. Because Killzone was a very linear game, the way we could approach it was that you have an area in which you have gameplay, shoot some guys, and then there's a corridor. You walk into the corridor, the door closes behind you, you walk along the corridor, and while you walk, all parts of the level is streamed out, the new level is streamed in. So you could have very big levels, but they all had to be linear in capacity. And yeah, for Horizon, that was definitely not good enough. We need to build something absolutely new. And the way we approached it is that we divided our world into two different types of data structures. First of all, we organized the world into tiles. So a tile is, well, it's organized in a fixed size grid, and a tile contains pretty much only geometry. And the way its tiles are streamed in depend on the player's distance from each tile. So this is a relatively simple concept. What's more interesting are the scenes. So a scene is a collection of objects that can spawn in the world. So mostly entities, but also geometry, particle effects, these kind of things. And each scene contains a state machine, which determines its behavior. So once the scene streams in and activates, the state machine starts running. It reacts to messages which are relevant to whatever is happening in the scene and can modify its behavior or modify the behavior of the whole game. And the way we manage streaming there is that the size of a scene is defined by the user. So a designer can determine how big a scene is, when it should stream in, and it's all about trial and error, but it actually was good enough for our purposes. So what you see here is our 3D editor, something we actually also built customly for Horizon, because in Killzone we used to use Maya as our game editor, which is a bad idea, don't do that. So we built something completely new for our 3D view, and the ring that you see on the screen is a scene. Essentially, that's its outer size. So when the player enters that ring, the scene will stream in and then will activate. It will populate the game world with things which are right now represented by icons. So these are if I remember correctly, some sort of sequence networks in this case. So there was a bunch of conversations which would be possible for the player to get into once walking into that specific scene. Now, the thing is that that was cool, but there was still one problem that we needed to deal with. So again, we are making a role-playing game, so items are relevant. So what would happen if you had a quest which involves an item which is on the other side of the world? So how should the game behave if you need to pick up an item and it should tell you more or less where that item is, but the item is not streamed in? I mean, if you streamed it in, then suddenly if you open enough quests, you stream in the whole game and you run out of memory. So what we did, we introduced a concept that we called baking. So the way it works is that when you place an item in the world, you need to place it as part of a scene. Our editor would pick up that certain items are referenced by quests. And that means that these scenes, which contain these items which are referenced by quests, would store the information only about their UID and their location. So that means that we had a constantly loaded mapping between some UIDs representing items and their locations. And the way the system worked is that if the item was streamed out, you would use that mapping to point the pin to the location where you need to go. And the moment the item got streamed in, that pin would get removed and it would get pointed on the streamed in item. And when you walk out and the item gets streamed in, the exact inverse would happen. Okay, game saves and data management. Well, that thankfully is not like the biggest problem that you need to solve. So the problem was the game is big, and if you want to save everything, you will run out of storage quickly. And now in Killzone, we did save the whole state of the level, which made it a little bit more complicated for us. So if you saved a game in Killzone, essentially the state of every alive entity and some other additional systems was saved to disk. But the thing is that if you have like 1,000 entities, it's still a couple of kilobytes of data. But if these entities get multiplied into millions and hundreds of millions, then you run out of space quickly. So we need to approach it in a totally different way. And we actually did something relatively radical. So what we did is that we decided to save only 4 systems. The player inventory, so we save what items you have. The player character progression, so the skills, the perks, the character level, experience, yada, yada, yada. We would save the quest system, so the state of all the quests. And we would save something new, which we called the fact database. So what is our fact database? Well, it's essentially a big container of global variables. So we introduced a concept of facts, which are strongly typed, user-generated, by user I mean designer-generated variables. And these facts can be used in scripts and can also be used in some systems. So you would define a fact, and that fact would be written to by a specific system. And that meant we have very strict control on what is being saved, and actually it was good enough. Also, what was relevant is that we forced that states of all the scripts that were run in the game should be based on facts. So you only save the fact database to disk, and every single script needs to be able to restore based solely on information in facts. And that actually was a bit fiddly, but was good enough for our purposes. Now, our introduction of facts actually had a very interesting consequence and very beneficial for us. What happened is that we noticed that a lot of role-playing games tend to use conditional systems. So you have like a piece of script which runs in a loop and is attached to a specific system, like spawning, conversations, quests, and essentially checks for some sort of a change in the world, right? So, I don't know, you killed some entity, some player, some important character, and that has consequences for other systems. And usually that's done by running a script in a loop. And that's fine until your world is gigantic and you cannot run all these scripts all the time because you'll just run out of processing power. So what we did is that we introduced a concept of a condition. And a condition is a special script which only uses facts as data and returns a Boolean value. And the way it worked is that each time a new condition was created, it would get registered in the fact database, which facts it's interested in, and the fact database, upon changing that fact, would notify all listening conditions that that fact got modified. So in the end, instead of running everything in the loop, we got this elaborate condition system which runs on demand, making the whole thing much, much more efficient. So, to sum this up, to build Horizon Zero Dawn, we didn't need to fundamentally rebuild the engine. We essentially decided to rebuild certain smaller parts to improve others, and essentially we managed to put the next generation of our engine like that. Now the thing is that although we made an effort to reuse as many of the old systems as possible, elements that were no longer fit for our new purposes were mercilessly removed. Thirdly, component-based design and uses of its messages made it really easy to add functionality in iterations. One good example of that is that if we were phasing out old functionality, but some people relied on it, at least for prototyping phase, we could introduce new functionality gradually and isolate the old functionality to a component. So once we have the new functionality done, we can just remove a component, all the data with it, and people can use the new stuff. And finally, working on low and high-level systems, and as well as tools and content at the same time, is literally like building a plane while flying it, but in the end, it is possible to do that. So that's pretty much it. Thank you very much for listening. Thank you a lot for coming. And if you have any questions, I'd be happy to answer them.
Okay, so do you have any questions? Thank you for the talk.
Hi, so it's nice, gorgeous. Sadly, it's not for PC.
Sorry?
Sadly, it's not yet for PC, hopefully soon.
Ever.
Come on, man, don't be rude. Okay, so my question is this. You compared, when you were explaining your engine, you compare it to Unreal Engine. And you say some engines already have these features and they're using messaging system and this. So why not just use other engine? That's one question. And second question, on what engine you actually based your engine?
Okay, so first of all, you were asking if a lot of functionality that we have was based on Unreal Engine or other engines, why didn't we use Unreal Engine in the first place? And the second question, if I understand correctly, was you were asking, oh shit,
what engine you based your engine?
Well, okay, so first of all, the engine is old, right? It's 13 years old, and that's essentially, we're talking Unreal 1 times, right? So the technology we've been building over these 13 years, and given that we have a very specific purpose, we are building the games specifically for PlayStation, and nobody else, like no third-party engines do that. So by doing that, we can exploit functionalities that nobody else can. And by that, we can have our own engine, meaning we can have our own workflows. Because we all know that if we are reusing the engine, a third-party engine, at some point you notice, hey, this game was built on this game was built on this. And if you have your own, that's not the case. You're being unique. So first reason was we had a lot of technology base, so switching all of our workflow to a different engine would actually be more work than updating this one. Plus, yeah, we do have some artistic benefits for using our own technology. Second of all, we did base a lot of our design decisions, mostly along tools, not necessarily about functionality in the core systems, but mostly about tools on Unreal Engine, but also other things. When we were making our tools, Unreal Engine was just being announced, and they were promoting a lot of stuff very well. And they did a lot of cool stuff, that's true. So we were essentially looking at mostly Unreal about like scripting, for example, to build our own.
Thank you.
Thank you.
Hi. I'm actually from Warhorse Studios, and we probably solved a lot of problems that you had since we moved from a first-person engine to a first-person shooter engine to an RPG. And what I'm probably mostly interested in is the scripting system. Can you maybe expand on it a bit? I mean, was there an option, for example, to test the scripts right away since you were using C++? So did you have any interpreter or something along those lines?
No, not really. So the only thing that you can, I mean, you cannot really test a script that touches game content without running the game, right? So you need to go through a whole process, compiling script, running the game, and then running it. We do have some testing of correctness of data. So for example, if the script references an entity, and somebody removes that entity while editing, you know, some other person on somebody else's work machine, the editor will pick up, hey, this script is referencing this entity, so if you're removing this, you're breaking that script. So these kind of links between data, that's something we could catch at editing time. Of course, compilation also fixed some issues, but testing would not really. The only thing that we could do is that we have a functionality that when a script is running in game, you can actually tweak it in the editor, and the game will pick up the modified script to an extent.
Right. So if I understood it correctly, you can actually tweak the script. It will create the graph box, and then you can use it in the editor right away. I mean the box and the connective graph.
In that direction. So pretty much. Essentially what happens is that you need to create a script function in the source code of a game. You need to create a specific resource in the editor, and that at that moment the whole thing is usable. So introducing a new scripting function, a new node, if you know exactly what you want, of course, right? Takes, I don't know, like 10 minutes.
And maybe last question, did you have problems fighting your scripters? I mean, they would probably have to have, let's say, a bigger programming background than usual.
Well, we have a big stick. But more seriously, no, not really. I mean, our designers are surprisingly technical, so their scripts are not very pretty, but they are kind of ingenious. Maybe that's not the word. They can get stuff done. They're not confused by programming in a visual way. So we didn't have these kind of issues. We, of course, have some back and forth about functionality, debugging, and so on and so forth, but I don't think we encountered anything major.
Right. I appreciate the use of the word ingenious. Okay, thank you.
Okay, we still have time.
Hello. You said that you had some checks in the scripts that make sure that when you reference entity that has been removed, you somehow detect it. So does that mean that you have to have the entire world loaded in your editor to do this? I
guess. The idea is that the editor just does that. So you open a script in your editor, and the editor actually helps you find game object you're referencing to. So there's like a drop-down box and does filtering. Hey, I'm looking for entities, I'm looking for items, so on and so forth. And
but how does the editor know what entities exists? And
we have a database running. So essentially we have a daemon running constantly and analyzing all the game data and updating it relatively periodically.
And just one last question, the daemon, does it use like SQL database engine, or is it completely your own?
I actually cannot answer that question, but it's mostly because I didn't work on the daemon, so I just don't know. I think it's something relatively standard, but what exactly, I'm not sure.
Okay, thanks.
Just one more question. Can I get your notes? There was a lot of links, and I would like to see them.
Yeah, I'm kind of hoping that the whole thing will be available to you all. If the conference doesn't do it, I'll put it on some website.
Okay, great. Thank you.
I saw one more over there.
Hi.
Okay.
Hi, thanks for a really interesting talk.
Thank you.
I was wondering, after having worked on the same franchise for a long time with Killzone and jumping into new, completely new IP with a new game, how do you manage kind of like the excitement in the team from like working in the same thing for a long time and also switching to something new? Like, was the like a huge desire within the team to work on something new? Was the kind of like a bit of resistance in the sense of like, oh, we really like this world and we work
So the way it worked is that most people, like 99.9%, were super happy. We've been doing like super dark for sci-fi first-person shooters for a decade. It's kind of cool to do something else every now and then, right? So most people were happy. There were, of course, a bunch of people who are really into first-person shooters, but that's like a handful. So most of the studio was definitely very happy to work on something new.
How long took you to like make some working prototype of this game before you realized, okay, let's do some big changes? Did you actually make some prototype, or how was the developing progress? And actually, how long it took you to make the whole game?
Okay, so the answer to your question would be much more better answered by our managing director, who actually did a presentation about that specific thing. So I'll just sum it up very quickly. The way it worked is that at some point during Killzone 3, we had this idea to do something totally new, and we did some internal pitches about ideas. We selected a few and made a couple of prototypes. And this went on ice for a little bit, and after some, we revisited these ideas and decided this idea, which we called Horizons, the coolest one, and just go with that. And after that, there was years of prototype.
Does your engine support, let's say, getting right into the game, or if you change the scripts, change the graph, you have to run the binary again to see it all working?
No, we support hot loading of pretty much all data. Not everything works perfectly, but again, like 90% of data, you can tweak it in the editor, press a button, and it shows up in the game.
So basically you have like a PS4 or whatever running by your computer and you hot load it into the PS4? Or you have, do you have a PC build? No, it cannot be run at all at a PC, right?
So the thing is, we do work with dev kits, and stuff gets communicated between our workstation and the dev kit and the editors. Of course, on the dev kit, the game is on the editor is of course on the PC. The game is of course on the dev kit, and there's communication between going on.
So another question is, how big is your team? And then I have another question after that.
It varies over time, obviously, but it's about 200 people.
And I got another question idea, thanks to his question. Okay, so you don't have it now for PC. Are you actually planning to expand on other platforms, Nintendo Switch, Xbox, and these things?
Really, the questions about platforms are kind of moot. Guerrilla Games is owned by Sony.
Oh. Okay, got it.
All right, I don't want to squeeze Leszek for more answers.
Sure. Well.
So thank you very much for your talk.
Thank you very much.